Hello everybody, welcome to today's lesson where we're going to talk about how to use random samples to compare a couple different populations. Our learning target today is I can compare populations using multiple random samples. Okay, this first sentence here is important because it's essentially what we're going to be doing today. It says you don't need to have all the data from two populations to make a comparison. That's like saying, if I were to take a class poll, I don't need the entire class. I could take a portion, a random sample of that class to make comparisons. Okay, and I could probably get pretty accurate data depending on how many people that I survey, right? So let's take a look at a couple of these examples. For our first example, it says 2 bags each contain 1,000 numbered tiles. So here's bag A and here's bag B, and they have numbered tiles in them. It says the double box and whisker plot represents a random sample of 12 numbers from each bag. Compare the samples using measures of center and variation. And can you determine which bag contains tiles with greater numbers? All right, that's kind of a wordy sentence there, or paragraph. A lot of these are. So if you need to reread that, please feel free to do so that you have a good understanding. But basically, we're comparing these two bags and seeing, can we determine which of them has greater numbers in the bags from the data that we picked. All right. Remember, when we're looking for measures of center and variation, I'm trying to determine, am I going to use the median and the interquartile range, or am I going to use the mean and the mean absolute deviation? We abbreviate that MAD a lot, right? And the way I determine that is to see, is my data skewed? I use median and interquartile range if my data is skewed, and I use mean and mean absolute deviation if my data is symmetric, right? So looking at this, I'm seeing that my median is not in the middle of my box here, and this whisker right here is also longer. Looks like it's a similar case here. My median is not exactly in the center of my box, and my right whisker is bigger. So I'm going to say that both distributions are skewed to the right, so I'm going to use the median and the interquartile range here. And we're going to find those for both bag A and bag B, and then we're going to see if we can compare them. So the median for bag A, that is at, remember this middle line in the box is our median, so that is at 4. And the interquartile range is the difference between the ends of the boxes. So 6 minus 3 would give me 3. So there's a range of 3, right? Remember, this inside the box represents 50% of our data. So a lot of our numbers, half of our numbers, are between 3 and 6. Then we go to the median for box B is at 3. And the interquartile range, oops, I already have that written over here, is the difference between the ends of the boxes. So 5 minus 2, which is 3. So you'll notice that our interquartile range is 3 for both of them. So our variation is the same for both of the bags. And the median for bag A is 4 versus 3 for bag B. So with the little data that we have, it looks at a glance like bag A has the bigger median, but do you think that we can determine which bag contains tiles with greater numbers? That's the question. And I'm going to argue that no, you can't. And the reason that I'm going to say no is because look at our sample size. We only picked 12 different numbers out of this bag of 1,000 number tiles. And to me, that sample size is too small to say that bag A has greater numbers than bag B. So I'm going to say that the sample size is too small. Remember, a good rule of thumb to use is use at least around 30 samples is usually a good rule of thumb to follow as kind of like a minimum. So I'm going to say, can you determine? I'm going to say no, you can't determine. The sample size is a little bit too small. It looks like it's generally larger. The bag A contains generally larger numbers. And if this said something like 50 numbers, then I would probably say yes, that in general, we have bigger numbers for bag A. But since we don't, I'm going to say no, our sample size is too small. All right, let's move on to the triad here. And I'd like you to pause the video now, read through the problem, and try it out on your own first, please. Okay, let's come back here to see how we did. I'm going to kind of work through this triad problem just to see if you come up with the same results here. Just because it's a different type of data, here we have a double dot plot. So I'm going to kind of work through that with you. The double dot plot shows the weekly reading habits of a random sample of 10 students in each of 2 schools. Okay. Compare the samples using measures of center and variation, and then can you determine which school students read less and explain? So some of you are probably already saying right away, whoa, pause. We only sampled 10 students. That's less than what the 30 you said, Mr. Gillis. So yeah, that is true. So you're probably going to say the same thing, is that the sample size is too small to make a valid conclusion. But it still needs you to compare the samples using measure of center and variation. Okay, so I go back up here and I think, am I going to use the median in the interquartile range, or am I going to use the mean in the mean absolute deviation? Well, it looks like here I have some pretty symmetric data. I've kind of got the bell-shaped curve going on here. I'm going to say that this data is pretty symmetric. So I'm going to use the mean and the mean absolute deviation for school A and for school B. And we'll kind of compare our data, and then we can kind of get at how much sample size we have. So for the mean for school A, that's the average. Remember, we need to add up our numbers and divide by how many there are. Well, there's 10. So we know we're going to be dividing by 10. 0 plus 0 is 0. So plus 1 is 1. Plus 2 is 3. Plus another 2 is 5. Plus 3 is 8. Plus 3 is 11. Plus 4 is 15. Plus this 5 and this 5 is 10. So 25. And then 25 divided by 10 would be 2.5 for our average for A. And then let's do B as well. Again, I know there were 10 students sampled, so I'm going to divide by 10. And then I'm just going to add up my numbers here. So I have 0 plus 2 plus 3 plus 3 plus 3 plus 4 plus 4 plus 4 plus 5 plus 7 gives me a total of 35. And 35 divided by 10 would be 3.5. So my average reading time in hours for school B is 3.5 hours, whereas the average reading time in hours for school A was only 2.5 hours. Okay, so that's comparing their averages. Now let's determine how much variation is there. So the mean absolute deviation, remember, is how much on average do these points, how far away are they from the average? Okay, so let's do that. Here we have my average is 2.5, so how far away is 0 from 2.5? Well, it's 2.5 away, and I have 2 of them. How far is 1 away from 2.5? Well, it's 1.5 away. How far is 2 away from 2.5? A half, so 0.5 plus 0.5. 3 is also 0.5 away, and I have 2 of them. Plus 4 is 1.5 away from 2.5. Plus 5 is 2.5 away, and I have 2 of them. Okay, so let's add that together. 2.5 plus 2.5 plus 1.5 plus 0.5 plus 0.5 plus 0.5 plus 0.5 plus 1.5 plus 2.5 plus 2.5. When I add that together, that gives me a total of 15 divided by, well, there was 10 entries, so 1.5 is my mean absolute deviation. That means on average, each one of these points is 1.5 away from the average. So they're 1.5 away from 2.5. And then I'm going to do the same for letter B here. I'm not going to painfully bring you through it. I'm just going to tell you that the mean absolute deviation you should have got was 1.3. So on average, these points here vary 1.3 away from 3.5. And again, our data is, our variation is very close. Our mean is pretty close. I would say that it looks like the mean is a little bit bigger for school B. But again, when it says, can you determine which of the students read less and explain? I would say no, just like we said up here, because the sample size is too small. They only sampled 10 students in each of the schools. We would like to see at least 30 sampled would be a good rule of thumb. Let me know if you have any questions on how to do any of that, and I'll be glad to help you. All right, moving on to example 2. It says using multiple random samples. This double box and whisker plot represents the medians of 50 random samples of 12 numbers from each bag in example 1. So now we get 50 random samples. Okay, now I think we have a lot more information here than what we did the first time, right? So it represents the medians of each sample of 12, okay? So it asks us to compare the variabilities in the sample medians to the variability of the samples in example 1, okay? And then let's see what we come up with. So again, we've got, let me switch colors here. We're going to use median and interquartile range, just like we did for the first one, because we want to compare that to the first example. And then we have bag A, and we have bag B. What is our median of bag A? It looks like bag A's median is between 5 and 6, so 5.5. And the interquartile range, how much is between the boxes? 6 minus 5 would give us 1. And for letter B, looks like our median is 3.5. And our interquartile range is 4 minus 3, which is 1 as well. Okay, so now the interquartile range of the sample medians for each bag is 1, right? 1 and 1. And most of the sample medians for bag A are greater than the sample medians for B. So you see 5.5 to 3.5. It looks like this is a lot further to the right. The tiles in bag A, I would say, generally have a greater number or larger numbers than the tiles in bag B. And this time we have enough. We have 50 random samples, which is definitely higher than 30. That's good. So we can say this time for sure that bag A generally have the greater numbers. Let me just write that down. Than tiles in bag B. Okay. All right, number 2 says, what if each value in the box and whisker plot of the sample medians for bag A decreases by 2? So each of the values decreases by 2. Does this change your answer? Well, if my median decreased by 2, it would be the same as B. So then would they generally be bigger? Definitely not. So does this change your answer? Yes, this changes my answer. They'd probably be closer to the same, and there would be no difference with greater numbers. All right, last one here, and then we'll be finished. It says the double box and whisker plot represents the medians of 50 random samples of 10 speeding tickets issued in 2 states. Okay. So we have 50 random samples here. Compare the cost of speeding tickets in the 2 states. So let's look at our medians for state A and state B. And let's look also at our interquartile ranges. All right, for A, my median looks like it's at a little less than half, so I'm going to call it $54. Looks like it's the median price of a speeding ticket in state A. And in state B, it looks like it's right at $70. So it looks like that cost is more in state B for the median anyways. The interquartile range looks like we have about 60, I'm going to call it 67 minus about 48, it's close, to give me about 19. And for state B, I have about 77 minus, let's call that 67, about 10. Doesn't have to be exactly that if you can't quite tell, but I'm just kind of getting close there. And then let's compare. So it looks like the variation in state A is definitely greater. So these speeding tickets vary more, and you can see that this box is bigger than this box, meaning that these ticket prices vary a lot more, and we see that in our interquartile range. So the variation in state A is greater than in state B. And I'm going to say, and the measure of center, or the median, for state B is greater than in state A. This median is 70 compared to this median is 54. So this has more variation, but this is a greater median. So we can conclude that the cost of speeding tickets vary more in state A. So there's a lot more variability in state A. But generally speaking, in state B, they cost more. Okay, they're definitely further to the right. State B speeding tickets generally cost more. And we can conclude this because, look here, we have 50 random samples, and that should be valid data there. Right? That does it for this section. I just heard the noon bell, so I'm going to go grab some lunch. Thanks for watching this. Let me know if you have more questions. I'll see you guys later.